last speaker of the morning session, Mr. Sunil Kumar Pasupulati. So he is from IISER Thiruvananthapuram, and he will talk to us on the p-divisibility of class numbers of an infinite family of imaginary quadratic fields Q root D and Q root D plus 1. Please, Sunil, you can start now.
Thank you, ma'am. First, I would like to thank the organizers for the opportunity. And this is a joint work with Lakshmi Krishnamurthy. Okay, this is my usually actually my talk has two parts. One part I will be constructing a infinite family of quadratic fields whose class number is divisible by 2. Second part I will be constructing a pair of quadratic fields whose class number is the Q root D and Q root D plus 1 whose class number is divisible by 3. Okay. So first I'll introduce some notations and definitions. The K is number field, the finite extension of Q. OK is a numbering of K, integral closure of Z in K, and CLK is a class group of K. Actually, if you consider set of all fractional ideals of K, that is finitely generated modules of OK contained in K, with a binary aberration, it forms a group, and set of all principal fraction ideals forms a subgroup of it, and you consider the quotient. This quotient is a class group of number field K, and actually it is well celebrated. Result is that the class group is finite abelian group, and the order of this class group is defined to be class number of K. Okay. So the number the n I define to be norm on number field K, which is actually is a product of all Galois conjugates of an element. So it's very immediate from the definition is that if class number is 1, we can only OK is PID. And the ideal class group is actually the most basic and mysterious object in the algebraic number theory. The ideal class group is one of the most the complete list of imaginary quadratic fields with the class number 1 is given by Q root K, where K is one of them. And whereas for a real quadratic field there is no such list exists, but Gauss has conjectured that there exists infinitely many quadratic fields whose class number is 1, but it's still a conjecture. So understanding the class numbers, people have started looking at the divisibility of class numbers so that they'll understand the structure of a class group in the number fields. So even covalence heuristic predicts that the positive portion of imaginary quadratic fields, quadratic number fields, have a class number divisible by n. So it has been supported by several mathematicians, proving that there exists infinitely many quadratic fields whose class number is divisible by n for any n. So for example, there is Nagel, Ankni, Chawla, and Grass and such people. So many people have shown interest in the families like Q root of 1 minus mu x power n, where mu is equal to 1, 2, 3, 4. So we look at some of this kind of families first, and so Gross and Rolovich has proved that n greater than or equal to 3, where n is a prime. They have proved the class number of Q adjoint 1 minus 4 u power n is divisible by n. Even Stephen Lobotin has extended this result for any odd n. He is proving that Q adjoint 1 minus 4, class number of Q adjoint 1 minus 4 u power n, where u greater than 2 is divisible by n for any odd n. Okay, this theorem will come handy in one of our approach. And for n mu is equal to 1 case, Ramurthy has proved that whenever u power n minus 1 is a square root integer, he has proved that Q adjoint 1 minus u power n is the class number of Q adjoint 1 minus u power n is divisible by n for n. So now we will be looking at case mu is equal to 2. Recently, Azihul and Kalyan Chakraborty has proved that the class number of Q adjoint 1 minus 2 m power 3 is divisible by 3 for any odd integer m greater than 3. So we generalize this result and prove that whenever m is an odd prime power and p is any prime number, p is any odd prime, we'll prove that, and also the q adjoint root of 1 minus 2 m power p is not equal to qi. Then the class number of q adjoint 1 minus 2 m power p is divisible by p. The condition that I have here is that q adjoint 1 minus 2 m power p is not equal to qi. Is just that I am making sure that 2 m power p minus 1 is not a square. Okay. So once the similar problem, one of other interesting problem was looking at pair of quadratic forms whose class number is divisible by a particular number. So in the same spread, the IISER has proved that in 2018 there exists infinite family of pairs of quadratic imaginary fields q root t and q root t plus 1 whose class number is divisible by 3. So he also conjectured, based on this theorem, he has also conjectured that for any prime p and a positive integer n, there exists infinitely many prime n plus 1 successive real or quadratic imaginary quadratic fields q root t plus 1, q root t plus n, where t belongs to n, which the class numbers are divisible by p. So here I'll be actually proving IISER's conjecture for n is equal to 1. So this is what like for any odd prime p greater than or equal to 3, there exists a infinite family of pairs of quadratic fields q root t and q root t plus 1 where t belongs to Z, whose class number is divisible. This is what I'll be proving it first, and then later on I'll prove my main theorem one. Okay. Before getting into the proof of this theorem, we'll just check the infiniteness of the family that I gave in the main theorem one. So what I want to if I consider set of all m such that p divides the class number of 1 minus root of 1 minus 2 m power p. So if m to be in this, yes, this should not be root of this should not satisfy this equation for any y. But we know that by Siegel theorem, this particular equation has only finitely many solutions. So S contains all odd powers but finitely many. All but finitely many odd powers. So this implies that the family that we have proved in the theorem 1 is actually infinite family, and now we'll get to construct. Now we'll construct a consecutive integers t and d plus 1 such that p divides the class q root t and q root t plus 1. Okay. So by main theorem 1, we know that p divides the class number of this. But this thing can be also written as this. It's just I'm sending 4 inside and taking power p is just the same as this. And okay, let's keep this aside and then look at. Now let's take u is equal to 2m power p minus 1, and now apply Stephen-Lobotian result that I have stated in the starting. It gives me that p divides the class number of q adjoint root of 1 minus 4 u power p. So now we look at, but let's look at what is this q adjoint 1 minus 4 u power p. If you look at this is actually comes out to be something like this. And now choosing d is equal to 4 into 1 minus 2 m power p whole power p, we actually have that the prime p divides the class number of q root t and q root t plus 1. Okay. This proves the main theorem 2, and now I'm just left with proving the main theorem 1, which is constructing an infinite family whose class number is divisible. Okay. Let's look at that. The proof of main theorem 1. So let's say d is a coefficient part of 1 minus 2 m power p with a signature. Then k is equal to q root. With a set k is equal to q root. So idea of this proof is actually we construct an ideal I such that I power p is going to be a principal ideal, and then we'll show that I can't be the principal ideal. So p divides the order of a class group, which means p divides the class number. That's what the idea is. So let me consider alpha to be 1 plus root of 1 minus 2 m power p. Then the norm of alpha is equal to 2 m power p. And also consider since norm of alpha is 2 m power p, then the only primes that divide alpha that appear in the factorization of alpha will be the primes that lie above 2 and the primes that lie above p. Sorry, m. That is actually, yeah, since m is a prime power, like if you consider it is a prime power of q, then the only prime that appear in the factorization of alpha will be the primes that lie over 2 and the prime that lie over q. Okay. Okay. Since D is congruent to 3 mod 4, the ideal 2 is ramified, so there exists an ideal P in OK such that ideal generated by 2 is actually equal to P square. Okay. So now, as I said, we'll write the if since I said only primes that lie over that appear in the factorization of alpha will be P and Q. So like if factorization of alpha will be if it is like P into Q power T, then look at norm of alpha, like norm of ideal alpha, it comes out to be 2 into Q power T. But see, observe that since see, now we have it is actually 2 Q power T is equal to 2 M power P. I can write R. So P divides T. So now set an ideal I is equal to P into Q power T by T. Okay. So now look at the power of this ideal I, that comes out to be a principal ideal. Okay. So now my aim is to prove that this ideal, I will prove that this ideal I is not a principal ideal. Okay, if suppose this ideal is supposed to be in principal ideal, then what happens? If I is a principal ideal, then beta power P is equal to ideal generated by 2 power P minus 1 by 2 into alpha. Okay. So since I was already assumed this K is not equal to Q of I, and also since D is congruent to 3 mod 4, so this also can't be equal to Q adjoint minus 3. So the only roots of K are 1 comma minus 1. So this implies I is not a principal ideal if this is not a power of a P. Because if this happens to be principal ideal, then what happens? Then I'll have that P minus 1 by 2 of alpha is equal to plus or minus beta power 2. So if I had to prove that P is not a principal ideal, it is enough to prove that plus or minus 2 P minus 1 by 2 alpha is not a pth power of any algebraic integer in OK. It's enough. Okay. So the next lemma will show you that this is not a pth power. So this will now I'm just left with proving this 2 into plus or minus 2 power P minus 1 by 2 alpha is not a pth power in OK. Okay. Let's proceed next. So the proposition, this proposition, the same conditions as the main theorem. Now I will prove that plus or minus 2 power P minus 1 by 2 alpha is not a pth power. Okay. So observe that minus 2 power P minus 1 by 2 alpha is a pth power if and only plus means 2 power P minus 1 by 2 alpha is a pth power. So now with this I'll say it's enough to prove that 2 power P minus 1 by 2 alpha is not a pth power. Okay. Suppose it's a pth power of some algebraic integer beta. Okay. Then we apply binomial theorem on one side, and one side we'll just see what we'll substitute what alpha is, and then combining the constant terms, we'll have 2 power P minus 1 by 2 is equal to this. So, but observe that A appears in every term in this summation. So we take A out, and this will imply that 2 power P A divides the 2 power P minus 1 by 2. Okay. So there are two cases we'll consider. One is A is even, later I'll deal with A is an odd case. Okay. So if A is even, then substituting this, looking at equation 1 that was, and then applying norms on both sides, I'll have 2 m power P is equal to A square minus B square D whole power. So since I know that A is even, 2 divides A and 2 divides 2m, so 2 divides B square D as well. So this implies, since D happens to be the positive part of 1 minus 2 m power P, which is an odd number, so D is also odd. So 2 divides B. Okay. So now 2 divides B and 2 divides A, so 4 divides A square and B square, which implies 4 divides 2m, which means 4 divides 2m, which means 2 divides m, but M we have taken is the odd power, which is not a, which contradicts the assumption that A is even. Suppose now let's consider the case A is odd. If A is odd and A also divides at 2 power, which means A has to be plus or minus 1. Now putting this into equation 3, which is something which looks like this, and then again applying the norm on both sides, we'll have 2m power p is equal to 1 minus b square d whole power p. We just rewrite this equation like considering taking capital D is equal to minus d and m as a like power of prime q, we'll have 1 plus db square is equal to 2m to 2 q power r. And as I said in the starting, since 1 minus 2m power p is equal to 1, this d we have taken to be square root part of 1 minus 2m power p, which means I can write 1 minus 2m power p is equal to some b dash square into d. Okay, just again taking minus d is equal to capital D and replacing this, I'll have 1 plus b dash square d is equal to 2m 2 q r square. Okay, these two equations imply that b comma r and b dash comma rp are solutions of 1 plus x square b. Okay, maybe I'll just change the slide. That will be more. Okay. These two equations will give me it shows that there are two solutions for bx square plus 1 is equal to 2 q power 1. But actually this lemma is simple consequence of the results of Sore and Bugard, where it says that for any odd prime q on an integer d greater than 3, the equation dx square plus 1 is equal to 2 q power y has at most one solution. But so whatever the cases, then when A is R, we could get two solutions for this equation, which is a contradiction. So this plus or minus 2 p power p minus 1 by 2 alpha is not a p powering, okay, which proves our main theorem. I will not be giving the proof of this lemma, but that is a simple consequence. These are my references. This is a paper where the results of the dependent equation are. And thank you.
Thank you, Sunil. So if you have any questions from the audience, please ask.
Yes, I have a question.
Yeah, please.
Yeah, Sunil, can you please go back to the slide where you have referred to the result of Lobotin?
Yeah, sure. Yeah. Chitra, can you just...
Yeah. No, yeah, this one.
Yeah.
So actually Lobotin has proved that for k any odd number. So I hope you are aware of the result of Ankeny and Chawla that gives us that for any given integer k, there are infinitely many imaginary quadratic fields with class number divisible by k.
Yeah.
Yeah, so you can just take those elements as u.
Yeah.
And consider q square root minus 4u to the power k.
Yeah,
Then that would be basically q square root minus u.
Exactly, yeah.
So my point is that you have made use of Lobotin's result to prove the particular case of Iizuka's conjecture. So that actually gets followed from Lobotin's result in just one shot, I guess, if I am not wrong.
Yes, it does. Like, it's kind of, I can say, yeah, it does. Similar.
Yeah, I could follow that you have used Azizul Haq and Kalyan Chakraborty's result to get a new family of fields whose class number is divisible by k, and then you manipulate.
Yeah.
That gives you a different family altogether. But
Exactly.
this particular case of Iizuka's result is being followed from Lobotin's.
Exactly, yeah.
Okay. Yeah, that's all I had to say.
Yeah, thank you.
Yeah, thank you.
Any other questions from the audience? if there is no other questions, then
I posted on chat. I posted on chat.
okay, posted on chat. Sorry.
Class numbers have applications to the problem of equiangular lines, and the work by Appleby, Bengtson, etc. And there is an expository article, very elementary level, 1804.08100. It is mine with Shiva Kumar and Chatterjee.
I'll look at it. Thank you.
Thank you. Does the speaker have any applications to tell us?
Application, I haven't looked at any of these applications.
Okay, fine. Thank you.
Are there any other questions? Okay. If not, then we can thank the speaker once again. Thank you, Sunil.
Yeah.